Okay, so we're now going to spend this video looking at integrals with vertical asymptotes, or unbounded integrals. And so let's take a look at this. So integrals of this type, we're talking about the function is continuous on an interval from a up to but not including b. And it has an infinite discontinuity or vertical asymptote at b. So at its endpoint it has an infinite discontinuity or vertical asymptote. So if I was going to draw this function from a to say b, then at b we would have some sort of vertical asymptote. I'm just going to draw a dashed vertical line there at b. And our function may look something like this. In other words, it might be going to positive infinity. Okay, so obviously there's a problem with just using the fundamental theorem of calculus, because if we're doing our little rectangles, right, way over here as our delta x gets smaller and smaller, right, as n goes to infinity in that limit process, these rectangles' heights would become unbounded, right, because as we get closer and closer to b, the functional values are just blowing up to infinity, right? So how can we handle this? Well, what we're going to do is, as you can see, we're going to look at the integral from a to some value t, where t is between a and b, so t will be some value right here. And now the integral from a to t will be, this area here, right? I can calculate that. So I'm going to calculate that area in terms of t. Remember, a and b are fixed values. And then I'm going to take the limit as t approaches b, notice, from the negative side. So t is going to get closer and closer to b from the negative side from below. If that limit exists, then that area is actually finite under that curve. And we say the integral converges. Similarly, we can have an infinite discontinuity at the lower endpoint a. In that case, we're going to approach a from the positive side. So if our vertical asymptote were here, you'd be going from t to b, right, from t to b, and we would be pushing t in this direction towards a from above or from the positive side. If that limit exists, then the improper integral is convergent. If the limit does not exist, again, the integral is divergent. Now, if we have function continuous on the interval from a to b, except for some value c where we have a vertical asymptote. In other words, the vertical asymptote is in the middle. We've got to split up the integral into two parts, right? This one will have the infinite discontinuity or vertical asymptote at the upper limit, so it would be like the top one here. And then this one would have at the lower limit, we'd have this one. So we'd have to split it up into two. It's kind of like the example we did at the end of the last video where we split the integral into two integrals. The improper integral into two integrals. So let's just take a look at this. And of course, let me just say in this case, this integral will be convergent provided both of these integrals are convergent. All right. The one trick about these, unlike the infinite limits, when we had infinity or minus infinity, we knew what to do. Here you've got to reason a little bit. Where is our infinite discontinuity? Do you remember how to determine where we have a vertical asymptote? It's where the numerator is not 0, but the denominator is 0. If I plug in 0, I get the cube root of -1. I get -1 down here. That's not a vertical asymptote. But if I plug in 1, there's the problem. 1 minus 1 is 0. I would be dividing by 0. That's undefined. So we have a vertical asymptote at x equal 1. So it's the upper limit where we have the problem. So in the upper limit case, what do? We're going to take the limit as t approaches, in this case, 1 from the negative side. And let's write this as x minus 1 to the 1/3 power. Okay. Now I could have done a u substitution here. But I'm going to do this u substitution in my head. Okay, and you could do it like we've done in the past, but I'm going to do it in my head. What's the antiderivative of 1 over x minus 1 to the 1/3? Well, remember, we're going to have to rewrite this. Maybe I'll do that. That will help a little bit. T going to 1 from the negative side, integral from 0 to t. This will be what? X minus 1 to the negative 1/3 power. So, you know, it's gonna be, you know, x minus 1 to the, add 1 2/3 power, divided by 2/3, so times 3/2. And then, you know, we don't have to worry about any adjustment because the derivative of what's inside is just 1, right? So when I take the derivative of that function, the antiderivative, I'll get back to this. If you do a u substitution, u is x minus 1, then du is just dx. So we can do this without, you know, sort of doing the substitution in our head, and it's very simple substitution. So I'm going to get 3/2 x minus 1 to the 2/3 power. That's my antiderivative. Just check this, right? If I take the derivative by the chain rule, bring the 2/3 down. 3/2 times 2/3 is 1. X minus 1 to what? Subtract 1, negative 1/3. And then the derivative of the inner function would just be 1, and I get exactly that. So remember, we're approaching 1 from the negative side. And so what do I get here? I'll pull this 3/2 out. I get t minus 1 to the 2/3 power minus 0 minus 1, just negative 1 to the 2/3 power. What is negative 1 to the 2/3 power? The 1/3 is the cube root. Cube root of negative 1 is negative 1, but then I square negative 1, I get positive 1. Or you can square negative 1 first and then take the cube root. Either way, we get 1. Well, is this limit exist? Is it approaching a value? Well, I can plug in directly. We're approaching 1 from the negative side, but I can plug in directly. This function here, t minus 1 to the 2/3 power, is continuous for all values of t. And so I can plug in directly. And what do I get? 1 minus 1 to the 2/3 minus 1. Of course, 1 minus 1, this is equal to 0. Right? So you can plug in directly, remember, with limits, because these are, notice we're taking limits not at infinity anymore, but we can plug in provided, you know, we get a real value output. 0 minus 1 is negative 1. I get negative 3/2. What's this mean? Integral converges. And why am I getting a negative number? Well, if you were to graph this function over the interval from 0 to 1, you would see that it's actually going to be below the x-axis. And so you're getting that negative area. That's what's happening. Okay. Let's try another one. Where's our problem here? Where do we have a vertical asymptote here? At 0 or at 2 or somewhere else? The vertical asymptote is at x equals 0. If I plug in x equals 0, I have division by 0. So this time, that's the lower limit, right? The lower limit, right, has the discontinuity. So we're going to take the limit as t approaches 0 from the positive side. So notice it does matter which side we're taking this limit at. So this is the limit as t approaches 0 from the positive side. And t now is our lower limit, right, to 2. And I'm going to rewrite this as a 1/4 x to the negative 3. 1 divided by 4x cubed is 1/4 x to the negative 3. Okay. What's the antiderivative of x to the negative 3? It's going to be x to the negative 2, right? Add 1 divided by negative 2. And let's clean that up before we evaluate it. This is going to be negative 1/8 and then 1 over x squared. So we have negative 1/8 over x squared if I clean all that up. And so what do I get at 2? 2 squared is 4. 4 times 8 is 32. And then minus a negative is plus 1 over 8t squared. So we've evaluated, so again, this limit sign has just been tagging along. I haven't applied it yet. We're just looking at this what's the value of this definite integral from t to 2. And the answer is it's this, right? For any value of t, I can plug in and get the value of that definite integral. And now we're going to push the limit to t going to 0 from the positive side. But if I plug in this time, what's going to happen? What's going to happen to this is t gets smaller and smaller. This quantity is going to get smaller and smaller. And 1 divided by a smaller and smaller quantity, notice it's squared, right? It's always, well, t is approaching 0 from the positive side. So this is always positive, but it's getting smaller and smaller and smaller, right? As t goes to 0. And this form of this limit is 1 divided by 0. Right? What does that mean? It means this thing is going to infinity. This thing is going to infinity. And negative 1/32 plus something going to infinity is what? Infinity, right? And so this integral diverges. This integral diverges. Okay. Look at a couple more examples. Now I've included the graph of both secant squared x and tangent x. You'll see why tangent x. Hopefully you realize why. But look at the graph of secant x, right? We're going from 0, and this is pi over 2 right here. This is x equal pi over 2, this vertical line. As we get closer and closer to pi over 2, right, secant has a vertical asymptote. Remember, secant's 1 over cosine. Cosine of pi over 2 is 0, and so that thing is getting closer, you know, as x gets closer and closer to pi over 2 from the side, this value of the secant function is blowing up. And so our problem is that upper limit, right? We have a vertical asymptote at the upper limit. So this is the limit as t goes to pi over 2 from what side? The positive or negative side? Which side are we approaching pi over 2? Negative side or positive side? Negative side, right? We're below pi over 2. We're approaching it from the negative side. So this is from 0 to t, secant squared x dx. Well, what's the antiderivative of secant squared x? Yeah, now you know I've got the graph of tangent x down here, right? The antiderivative of secant squared x is tangent x. So I can evaluate tangent of t, it's a little cumbersome, tangent of t, minus tangent of 0. And of course tangent of 0 is just 0. But what's happening as t approaches pi over 2 from the negative side of tangent of t? Well, I've got the graph of it right here. Again, this is x is equal to pi over 2. What's happening to the tangent function as we get closer to pi over 2 from below? It also is going to minus to infinity, rather, positive infinity. And so this limit is infinity, and this integral diverges. All right, last example for this one, we're going to take a look at one more. So the last two integrals diverge. The first one we did in this video was convergent. Let's see what happens with this one, and this one involves the log function. Where's our vertical asymptote here? I'm going to just show you the graph of the natural log function here. Do you remember? We looked at it. Where are we going to have trouble at? Yeah. Vertical asymptote at 0, right? As we get closer and closer to 0, we're dropping down. And this is vertical asymptote. We don't ever hit the y-axis here. So we have a vertical asymptote at 0. So the lower limit is the problem, right? Right there. And so this is going to be the limit as t approaches 0 from the positive or negative side. Think about that. It's going to be positive side. Okay. Well, now we got a problem. How do we find the antiderivative of natural log of x? Is that 1 over x? No, that's the derivative of natural log of x. We've done this already in class previously. Do you remember the technique we used? Yep. Integration by parts. Integration by parts, which I hope you're still practicing. So what are we going to choose u to be? Liate, log. Hey, log. What's dv? Is there anything left? Yeah, the dx. So what's du? 1 over x dx. What's v? Integrate x. So remember, integral of u dv is uv, so that's x times the natural log of x, minus the integral v du. What's going to happen there when I multiply v times du? X times 1 over x is what? 1. I'm just left with dx. What's this thing become? Antiderivative of 1 is just x. So there's my antiderivative using integration by parts. Antiderivative is x, natural log of x, minus x. So this is equal to the limit as t goes to 0 from the positive side of what? Let's evaluate this at 1. Well, what's the natural log of 1? 1 times the natural log of 1. What's the natural log of 1? What's the natural log of 1? 0, right? Natural log of 1 is 0. So that's 0 minus 1, so that just becomes negative 1. When I plug in 1, 0 minus 1. When I plug in t, so minus what? Evaluate at t, I get t times the natural log of t minus t. So let's clean this up a little bit. Limit as t approaches 0 from the positive side of negative 1 minus t natural log of t minus plus t. Okay, now as t approaches 0, I can certainly plug in here and I get 0. So this is clearly, this here is clearly going to 0. But what about this? T times the natural log of t. Well, let's take a look at this. Some might say, well, if I plug in t as 0, 0 times anything is 0, so it's 0, right? Well, not so fast. When we say limit as t approaches 0 from the positive side, we're guaranteed that t is never equal to 0. It's close to 0, but it's never equal to 0. So whenever, when we plug in, that's if we get a particular value. The reason I can't plug in is because what's natural log of 0? Natural log of 0, right? It's not defined. We have that vertical asymptote, right? And so you see the problem is as t is going to 0, the natural log of t is going to minus infinity. We're multiplying these things together. This thing's trying to make the product go to 0. This thing's trying to make the product go to negative infinity. Which one's going to win out? Sometimes it's 0, sometimes it's negative infinity, sometimes the limit could be something in between. Well, what we're going to do to evaluate this limit, if you remember, is use L'Hopital's rule, but it's not in the form we can use L'Hopital's rule. L'Hopital's rule is what? 0 over 0 or infinity over infinity. So if you remember, the way we could do this is, right, this is of the form 0 times infinity, negative infinity, right, but it's still infinity. That's indeterminate. But I can rewrite this in a form that I can use L'Hopital's rule. And the way to do that is I'm going to write this as the natural log of t divided by the reciprocal of t. Right? If I divide by 1 over t, that's the same thing as multiplying by t. These two expressions are the same. These two expressions are the same. But now what happens? The top is going to infinity. What's happening to the bottom? As t goes to 0, 1 over t also is going to infinity. It has a vertical asymptote at t equals 0. So now what's our form? Our form is infinity over infinity, and that's good, because now I can make use of what rule? You know what that stands for? L'Hopital's rule, right? So how does that work? I take the derivative of the top. What's the derivative of natural log of t? It's 1 over t. Over the derivative of the bottom. Now be careful here. What's the derivative of the bottom? 1 over t is equal to t to the negative 1. So remember, if I take the derivative with respect to t, we're not finding antiderivatives here. We bring the power down and subtract 1. So it's negative 1 over t squared. Okay. Now, before you do any plugging in to evaluate this limit, simplify this mess. Simplify it. So I've got 1 over t divided by this is times the reciprocal of 1 over t squared, or negative 1 over t squared. And if we look at that expression there, notice this t can cancel with one of these, and I'm just left with the limit as t goes to 0 from the positive side of negative t. Now I can just plug in directly. I get 0. Now I can plug in, right? I get 0. Again, I couldn't plug in here because natural log of 0 is not defined. Can't plug in directly, but I can now after using L'Hopital's rule. So all that, I'm sorry, for basically nothing? No, for something. It's 0. And so what's our final answer? The only thing left is the negative 1. And so our integral converges this time. So that's our last example, and yeah, that's a doozy, right? Because we had what? Let's go back to the beginning. What do we have there? We had integration by parts to find the antiderivative, and then after simplifying, we had to use L'Hopital's rule to find this limit, and not just L'Hopital's rule, but we had to get it set up to be able to use L'Hopital's rule. So quite a lot going on here. Okay, I'll have one more video that'll be short on this topic, and that'll be all that we talk about. But that's basically it. Improper integrals of two types. Ones with infinite limits of integration and ones with a vertical asymptote or infinite discontinuity.